little bit similar to what we saw yesterday, but for bounded neighborhood complexity, or linear neighborhood complexity. I think this is a nice thing, so maybe that I will wait till everybody's there, so that they can follow. And the other hour, which I will start now, and also in the end, maybe give you things which I did not have time to talk about in detail, so that if you want to explore more, and also that you have a feeling of what's going on in this research area. Yeah, and also, if I can, I would like to very briefly mention how people are now extending this whole theory to dense graphs, because this is what's going on right now. In fact, I will also show you a couple of papers on archive. Like, since January, there have been maybe 4 or 5 extremely interesting papers which came out on archive. So some of them even last week. So it's quite exciting, and it shows that this area is really lively at the moment. People are developing this theory. Tree depth covers, which is kind of reminiscent to what Arminder told on planar graphs and graphs excluding a minor. He said that, you remember maybe that he was layering the graph, planar graph, and then he was saying, look, if you take, so you kind of number these layers, and if you take all the layers, let's say I modulo some number, you remove them, what you get, the rest is has non-retrievals. So this is true for planar graphs. And then he said that, well, this is also true for graphs excluding minor. And actually something like that is also true for bounded expansion classes. And in fact, historically, this is what people were really interested in. So when Nechetril and Osuna de Mendes, they introduced bounded expansion in one paper, which I think came out in 2005 in archive and then was published in 2008. And so they defined it using these shadow minors, as we have seen. But immediately in that paper itself, they said that, see, this is equivalent to having these low tree width cover. And this is also equivalent to some other types of coverings. So I'll just define these things. So like this will, I will not go in depth. It's just for, for the culture, let's say. Because it is, historically, this was the start of this theory, and I think it's still nice and it has good application. Although it seems nowadays that this weak coloring number has taken over, and this is kind of more powerful technique, I think, these coloring numbers. But anyway. Okay. So what we had, just to remind you, so it started kind of, so there were two things. I think I've seen maybe 2003, but I'm not sure. Says that if you have a planar graph, where is this D, then the tree width, that's tree width at most 3D plus 2. And this property is called bounded local tree width. This is a nice thing, which, by the way, gives you nice implications for algorithms. For example, there is a very nice argument which gives you an FPT algorithm for dominating set on planar graphs using that. It goes as follows. So if your graph has a large radius, so this is your parameterized by solution size. If your graph has a large radius, you will find a long path, shortest path. But this shortest path will need a lot of vertices in the dominating set. So then that means if your radius is too big, you say, no, I cannot get a dominating set of size at most k. So it means the radius is, let's say, at most k. But that implies the tree width is small, and then you solve using D. Exactly. Exactly. It means these balls, these radius, conformal radius, they have small tree width. Planar graphs themselves have unbounded tree widths because of the grids, but the grids, you need to see the unbounded radius, So this is a really nice one. And if you look at this diagram, there's class called bounded local tree width, which extends bounded tree width, which they have this problem. So this is, by the way, not true. I think for if I don't make a mistake, bounded expansion classes don't have this problem, but they have the following one. So the corollary of this, and this was this layering Baker's technique called Baker's technique, due to Brenda Baker. I think she developed this in the late 80s or something to give some Peter's approximation algorithms for planar graphs, but this works for graphs of bounded local tree width generally. So then, so this Hamilton explained it last week also. So if you have a planar graph G and an integer p, you can color any integer p. One can color the vertices of your graph G with p plus 1 colors, such that for every I think most p colors, the subgraph induced by these I colors by any I color classes so essentially, so what you have to do, you have to leave at least one color out, right? But then you have bounded tree width. That's great.
Not a proper coloring, right?
In this case, it's not proper coloring. In fact, so if you take one color class, let's say I equals 1, what you get is a graph of tree width 5. So if we wanted a proper coloring, we would need tree width 0. If you could ensure that every color class, so if here it was I minus 1, I guess, instead of 3i plus 2, then you would actually get a proper coloring. And actually, I think we can get something like that.
But if it is not proper coloring, we can put lot of vertices in one color class, except say constant number of colors and vertices. Then
Oh, it should be true for any I color class. Right? So if you take this big color class, you do not have this problem. I mean, if you just keep this big one. So essentially, what it says is that any color class you remove, the rest has bounded tree. That's what it says, if you think of it. And this is also what Hamilton was explaining. How do you prove this? Well, you do this BFS. That's some vertex, and then you color, like 1, 2, 3, all these layers, you color them. And then, so up to P, and then once you reach P, we start at 1, 2, 3, etc. Okay. Now, any color class you remove, let's say you remove color class 3, it separates your graph into small pieces, and by this theorem here, this will have bounded tree. That's how it works. But this is specific to these planar graphs and also H minus and that. But actually,
so why is it called bounded tree with local tree?
Because locally you are bounded tree. Locally means distance at most d. If you take a ball of radius d, bounded tree. That's why it's bounded local tree. So tree width in general is not bounded, but locally is not tree width. Okay.
For that graph, tree width is bounded, you are saying, bounded by 3d plus 2. But the function of d, you are saying if d is true, that's d is
Oh yes, sorry. Yeah, but because it has radius d.
Because the function of d, that's what you are saying it's local.
The graph itself has radius d.
It has radius d, yes. So, okay, you can think of it differently. Take any planar graph. Take any subgraph of radius d. Like, you take any ball of radius d. This is also planar. Now it has radius d. Now it has bounded d. That's why it's bounded local. radius, a small radius. Take a small radius part, it has boundary radius. That's what it is. It's
Here,
straightforward.
what about this proper coloring? By coloring, you mean proper coloring only?
No, any color.
So you have two adjacent buttons can have same color.
Yes? That's what I'm doing here, right? I'm giving, so, I mean, this was covered last week, so I don't want to go too much into detail. Harmander explained it. So if you, basically, you take all the guys which are distance 1 of this particular vertex, you color them 1. Of course, they could be adjacent, right? This could be a cycle. Could be a cycle, or what could be, well, just like this, you could have, it is planar, of course, so, like this. What? Difficult. It doesn't really matter. Anyway, look, I don't want to go too much into details. I don't want to spend too much time because the idea is just to give you hints. If you want to study more on your own, that these things exist and you can go look for it. Okay, and well, this kind of colorings, we will call them low tree width coloring. Now this works for these players, but it turns out it also works for graph classes of boundary expansion. In fact, you can characterize it. So this will give us a new characterization of expansion. So, but before that, let me quickly define some refinement of tree width, which we call tree depth. Again, I will just define it so that I can explain it, so some of you might know it. What's the tree depth of a graph T? It is the smallest height of a tree T. Okay, so the height of tree being not the number of levels, but the number of edges when you root it. Okay, so this has height equals to 2. Or do we take, maybe we take actually the number of edges. I'm not sure. No, tree depth 1, I think are stars, so smallest height of a tree T, such that G is a subgraph of the closure. Okay, what does it mean? I'll give you a picture. So this is your tree T. What's the closure of the tree? The closure of the tree is you put an edge between any vertex and its ancestors. Okay, this is the closure of that tree. So what I want to hide my graph inside this. So I want it to be a subgraph of this thing. For example, let's take. This, and then I have a triangle. So this graph G is a subgraph of the closure. This is the closure. So now what you want to minimize this height. So over all possible trees, you'll try to find them.
What is specialization from?
Sorry?
What is specialization?
Purple? This is the closure. So these are the closure edges.
All the edges are drawn or you can.
So closure of trees contains. So you root it. By the way, I should have said rooted tree. In fact, it is rooted forest because you could have this. You're allowing disconnect. Rooted forest. Rooted forest means that okay, there could be several things which each of them has a different. This is just to allow disconnected things. If it's connected, you take the definition I had before. This want to talk about the tree depth, you should allow normally disconnected graphs, like tree width, right? When we talk about tree width, when we manipulate tree decompositions, we take connected trees, but of course you can do with a forest. Just do every tree independently. Okay. So
G subset of closure F, right?
G subset of, yeah, now it's a forest. Right. Okay, so for example, what's the graph of tree depth 0, no edges. Of tree depth 1, this is basically star forests. Right? Because when you take a graph of a tree depth 1 of height 1, just a star and there are no additional edges. The only thing you can do is a substar. Star, I mean, you could have, of course, manipulate things like this. So this is tree depth 1, the star forest.
What is related to the tree width parameter?
I will come to that. In fact, maybe I come to that exactly now. Yes. Observation. The tree width of G is at most the tree depth. So the tree depth is a refinement, you can see, of, say, of tree width. If you know you have tree width K, your tree depth might still be bigger. Why is that? Well, if you take your closure here, your forest. In fact, even better. Let me give you a whole chain of things. Vertex cover number of G. Tree depth of G. Equals the path width of G. Equals the tree width of G. I believe this is true. Maybe there are some other ones, but I think it's okay.
So when we have a forest and we take a closure, how do we like tree depth is the minimum among the heights of the
Yes. Correct. What is this? This is the vertex cover number, smaller size on vertex cover. This is the tree depth. So path width we didn't mention in the lecture, but it was in one of the exercises. So it's like tree width, but you force your tree to be a path. Okay. So this is more restrictive. Oh, sorry, it's all the opposite. Tree width is the smallest of those. The vertex cover is very large, so this is a set which, when you remove it, you have no edges. Path width, tree width, you know, and now tree depth I just introduced. So why is that? Let's see the first inequality. So a vertex cover, you have a small vertex cover, that means you have some set and everything else is an independent set. Then what do? Well, you can just, do the photo. So let's say this has size VC. You just take a path like this with VC vertices, and then you put lots of leaves. All these guys. Let's call this I. Now what's the closure of this? The closure of this is just here, you get a big clique. And these guys go upstairs. Of course this stays an independent set. But now you're completely free to put any edges that you had here, since this is a huge, everything's connected here. So the tree depth will be at most. So this is, the height is vertex cover minus 1 plus 1 vertex. Tree depth is at most vertex cover. So you can see that the path width is a refinement of tree width, the tree depth is a refinement of path width, we'll see that now, and the vertex cover is an even bigger refinement of tree depth. This, by the way, if you can find a vertex cover graph, this will give you a 3D composition. This can be useful sometimes. chain like that, you can. Okay. Why is the path width at most the tree depth? Well, you take the tree, well, the forest, let's take one component of the tree, so it will look something like that. So what's going to be my path decomposition? Well, I'm going to use these branches. So remember, this is restricted, right? This is tree depth. So the number of vertices in each branch is tree depth plus 1. And my path decomposition is just going to be this as a bag, and then this one, and then this one. So this will be the first. So I'll put, for every leaf of my tree, I will put one node in my tree position. And then these will be the bags. First bag, second bag, third bag, and so on. A path decomposition like this. Path decomposition. So this shows that the path width, remember what's the path width, is the largest size of the bags minus 1. The bags all have size 3 plus 1, so path width is at most 3. Sorry.
We did plus 1, why the plus 1 thing is coming?
This is the number of vertices. The height was the number of edges, so number of vertices. Alright, and then, well, for path width and tree width, it's trivial because path decomposition obviously is a tree width. So I'm not detailing that.
But the back size is like.
Tree width plus 1. Because this, I'm taking these paths have length tree depth plus 1. So that means okay, and bag, the path width is bag size minus 1. So tree depth plus 1 minus 1, which is tree depth. Okay, anyway, this is all not that important, it just allows me to state. I just want to state this characterization. And if you're interested in these things, I'm just giving the definitions so that you can explore more on your own. So this will not be part of the exam. You can stop listening. Okay, some definition, and then I can state that characterization of Pichetin and Posola and Mendes. So what's a P tree depth coloring? It's kind of what I said for the tree width coloring. P tree depth coloring. Okay, is a coloring. I'm not putting a bound on the number of colors. It's a coloring of G. But this time it will be a proper word. But this will follow from, I think, the definition, hopefully, of G such that for every I post P, any I color classes induce a subgraph of tree depth. And you see here, that's why in the tree depth definition I need to allow disconnected things, because I want to allow disconnected stuff. Notice that for essentially what I would like is that for one color class I get an independent set.
So it's a P plus 1 coloring.
No, the number of colors can be arbitrary.
Okay.
But you're fixing, this property should be for P.
Okay. Okay.
So for I equals 1, it should give me things of true depth 0. So then I guess it's a minus 1. Well, see, I'm not completely sure. So I didn't go too much into details, because I don't want to go too much into details in the class. I just want to show you that this exists, so that you can perhaps use, can be useful for you to know this. You can have the same notion for tree width. So these things are called low tree depth colorings or low tree width colorings. It's a coloring of G. Same thing but with tree width now. And finally, there is another notion of colorings. It's called a p-centered coloring. In fact, what they will show is that on bounded expansion graph classes, these things are all equivalent in some sense. And have to constants. G such that for every connected subgraph works as well. Of G, H of G. Okay, so the third notion of colorings is a bit strange. P-centered coloring. It's coloring of your graph. So if you take any connected subgraph of G, either it receives a lot of colors, strictly more than P. If it has a few colors, then one of these colors appears exactly once. Notice that these three definitions imply that you have a proper coloring. Because here, if you take a connected subgraph of size 1, it can receive only one color. What I'm saying, of size 2, so you take an edge basically. It cannot receive a lot of colors because there are just two vertices, but then one of the colors should appear just once, exactly once. So that means the two endpoints of the edge receive different colors. So this in particular implies the proper color. And these also because tree width 0 and tree depth 0 means independent sets. It doesn't matter if you don't catch the definitions. It takes maybe some time, and I don't want to give too many examples. I don't want to use this too much. I just want to state this nice characterization, which is the following. Maybe no. Just one small remark. For those of you who like colorings, remark that this definition and this definition generalizes two important types of coloring, which are called acyclic coloring and star coloring. So this, so for P equals to this one will be, I think, the star coloring, because that means any two color classes have treated one, which is collection of stars. So this is called a star coloring, if you know about that. And this one is called acyclic coloring. Acyclic coloring means it's a proper coloring, and any two color classes induce a forest. So these are nice generalizations of star colorings and acyclic colorings, which have been studied a lot since the 1980s. I mean, this even before this was introduced in the 1980s. This is probably in the 60s. So these are studied on their own, but they're also studied a lot to give bounds for other things. So you'll see many papers where they want to define some notion of coloring, and they use acyclic coloring as a method to give bounds on that strange coloring that they're defining. So it's kind of nice for people who do coloring that this theory embeds them in a sense. Jozef Nechetril and Patricio Soler-Mendes, also nicknamed POM, Patricio Soler-Mendes. So in 2005, I mean, the paper was published in 2008, I think. What they proved is the following. Let's see the class of graphs. And then another characterization which involves all these notions. The following are equivalent. C has bounded expansion. There's this function f1. Look at this statement. The kind of graph it's of Bounding expansion if and only if for every let's say p, standard reason p, for every integer p, so you have a function which for every integer p and for every graph, you can show that your graph has a p tree-depth coloring with not so many colors. So this time I'm bounding the colors, but it's some function of p. This is the same as having bounding expansion. That's what they showed. In particular, it implies, p tree-width coloring, because bounding tree-depth implies bounding tree-width. But actually, this is also equivalent. So you can rewrite this as bounding tree-depth. Even though this is weaker, it's still characterization. Finally, these p-center colorings. All of these things are equivalent. I don't know these colors too well. I have not studied them. Just for the definition. I didn't think too much about it because I've never worked with them since I didn't really prepare anything for this class. So just want to state the definitions. In fact, I mean, nowadays, people, I think people really mention these treated colorings because this is probably the strongest of these properties. I mean, even though they're all on expansion, but you can really work well with this one, especially for. So we saw. I mean, Hamid showed you that these things have algorithmic applications. You have this Baker's technique, which gives you approximation algorithms. You have this. He showed an FPT algorithm for subgraph isomorphism. So exactly what he showed would work here. Exactly the same thing. So you take your subgraph H, your graph H, which you want to check if it has there, it has a copy in your graph G, and you'll basically color you'll color, but you will fix P as to be probably the number of vertices in H, plus 1, maybe, something like that. No, yeah, just number of vertices of H. And then you know that any copy of H couldn't use more than P plus 1 colors. And this gives you an FPT algorithm. So this works also for exactly the same algorithm works for K. So these things all have very nice algorithmic applications. And then, why not working with tree depth, right? Because tree depth is so much stronger than tree width. So we might as well use tree depth rather than tree width. In particular, there are some problems which are solvable on bounded tree depth, but not on bounded tree width in FPT time. So why not use tree depth? It's stronger. And if you have bounded tree depth, you have bounded tree width. So as I said, historically, in that paper, where they introduced boundary expansion, they showed this theorem. And later, Zhu came up with this other characterization using the coloring numbers. And nowadays, if you look at, for example, if you look at the lecture notes given by the Philip Chuk brothers, they show this using the coloring numbers. So I think they show this characterization using the coloring numbers. So you can now, I think these coloring numbers are a nice tool, and you can derive everything using these ways, using these notions, instead of going through the shadow minors and doing these colorings. But this can be very useful, of course, in some applications. So it's not like it's useless. It depends on what you want to do, right? And exactly for these algorithmic techniques, this is very useful. So we have now seen, I think, 4 equivalent definitions of boundary expansion. The shadow minors, then we did the coloring numbers, then we did the neighborhood complexity, and now these low tree depth colorings and so on. So 4 equivalent things. So it really shows that you want to work with boundary expansion, choose any of these 4, whatever suits you best, and work with that. It's really powerful. And actually, there are more tools even, which I can maybe mention briefly at the end of the end. But I'm not sure if they give characterizations. There are more properties which are very nice, which can also be very helpful. Okay. But now maybe I want to go to maybe the last technical topic, let's say, of this lecture series, which is another nice application on these distance D dominating sets and distance D independent sets. And what we'll show is we'll show that there is some kind of so there's a nice, packing and covering duality between the two. And in fact, as you will see, there will be nice bounds which control them with each other if we have if we have, so now we will use the coloring numbers again. And this will give us this thing. So maybe I can state it here. Define what I want to talk about. So, the distance D dominating set. G. This is a D of vertices. Such that every vertex is D-dominated, which means it's a distance adjoining from somebody in D. Okay. So it's like the normal dominating set. But instead of distance 1, we will now know distance D. So if you take D equals 1, it is exactly the distance. And we have the corresponding notion of a distance D independent set. Distance D independent set. So I will deviate a little bit from the notation which is used in the literature in this thing because I'm more used to this one. So for me, distance D independent set means that any two vertices are distance at least D apart from each other. G is a set I for independent set of vertices of G such that any two vertices in I have distance at least D. So if you think of a normal independent set, it means D equals 2. Because everybody has distance at least. So if you look at the paper where this theorem is from, or the lecture notes from the lecture brothers, they use strictly bigger than D. But I don't find it that natural for this one, because I'm used to this one. Of course, it's equivalent, but it could be confusing if you look at the literature. Domination set is the same as domination set and independent set.
So if treated is bounded, then trivial is bounded. What is the converse?
No. So for example, a path has a large tree depth. A path of length n will have tree depth log n. So all these inequalities are strict. I mean, what I showed you. There's no bound for us. No constant. Remarks. Another remark is what? Maybe if you let me define the dominating D of G to be the size of the smallest D dominating set. And then D of G size of the largest independent set. So observe the following. If you have an independent set at distance D, let's say 2D plus 1, So if you know you have an independent set where so everybody has a distance at least 2D max plus 1. This is my independent set. If you take one vertex in your dominating set, now we were looking for this is an independent set, distance D plus 1. You're looking for a dominating set. Well, a vertex of your dominating set can dominate just one of them, right? Because if you draw the things which are distance, this is a ball of radius d. If you want to dominate this vertex, you have to be inside that space. But then you will have distance at least d plus 1 to this one, so you cannot dominate. So that means any dominating set at distance d is at least the size of an independent set of 2D plus 1. So if you take dominating set of size 1, the normal dominating sets, it's at least the size of an independent set at distance 3. Which is sometimes called packing or unpacking. I think somebody talked about this, no? Maybe too young. So this is so these notions are like dual in this sense. So this is a classic, packing and covering duality, which is very much studied in optimization and in particular using linear programming in optimization. So in these kind of things, when you have these kind of bounds, it's very nice if you could also find a bound for the other side. So the question is, can you find here some upper bound where you get a function of this one? Remember that for the strong and weak coloring numbers, we have this kind of relationship, right? And this is very nice because it basically tells us you can bound it one, you can bound the other. Right? Because that means you can replicate the bound here, and also this one will be squeezed in between some function of the dominating and some other dominating parameter. And well, I think this is not true in general. For bounding expansion classes, it will be true. There will be something like that. And this function will in fact be a constant. Well, not really a constant, it will be just something which doesn't depend on the number itself, it will just depend on d. And it will in fact be something which depends on the weak coloring number. So we will take weak coloring number to the square, and this will be your factor. So this is what I would like to show you. This theorem was proved by Volchak. Another check. So this funny R is pronounced J, if I'm not mistaken. It's Volchak. Wait, I'm sure I pronounced it incorrectly. Something like that. So what did he say? He said that, look, if you have a graph G, and you have a weak coloring sequence for 2D plus 1, then you can use this to build a dominating set and an independent set. I will give the precise numbers like this, and the independent set is not too large compared to the dominant set. So, G and now doing sigma, where the weak coloring number of this graph in the sigma is at most at distance 2d plus 1 is at most some constant c. There is an algorithm, a polytype algorithm, and the algorithm is quite simple. It's kind of a greedy algorithm. Building, what does it build? A D-dominating set of G, called D, a 2D plus 2 independent set of G, let's call it I, such that, so we know that we have this. I'll just put it in the chain of inequalities. Size of D will be at most C squared is I, C squared. So actually, it's a little slightly even stronger. Not only gives me an independent set as distance 2d plus 1. No, he gives me one at distance 2d plus 2, which is even stronger because the values are even a little bit more far. So we'll take the sequence, we'll use similar kind of arguments as we used yesterday, look at the weak reachability, we take the minimum, these kind of things. This will give us a dominating set, an independent set, and this gives a good approximation, because it's a polynomial time. Why? Because this dominating set is sandwiched between the independence number and the C squared times the independence number. And we can construct these two sets. So what does it mean? Okay, we need the coloring part, the sequence, coloring sequence. But we have seen before that if you have a graph class of boundary expansion, you can build these things efficiently. So as a corollary, you get that. If C has bounded expansion, one gets an approximation algorithm for D independent set and the independent set. Well, O of 1 is maybe this will depend on D. If D is constant, it's a constant. Because we know the recoloring number, the C in a boundary class of boundary expansion will depend on D. Note one thing, I just want to remark that in general this is not true. In fact, this D-dominating set, the independent set, if you want to, well, I don't know if it's true. I don't think it's true in general, but also, even for graph classes of boundary expansion, you can't compute them in FPT time, for example. So there is, in fact, I think the problem is, for those who know parameterized complexity, this is W1 hard, parameterized by the feedback vertex set. So for graphs of bounded tree width, part of the input. So if D is not constant, and you want to exactly compute one of these things, the independent set or the dominating set, D could be something which depends on n, the number of vertices. You cannot do this in FPT time when the parameter is the tree width, for example. So it is much like you cannot get good algorithms exactly, even in very special classes of bounded expansion like tree width, bounded tree width. This doesn't exist. But you have this nice f of d approximation algorithm, which is polynomial. So f of d approximation algorithm means that the solution you get is, for dominating set, is at most f of d larger than the optimal. And for the independent set, it's at least, you know, let's say 1 divided by f of d times the optimum size. So it's not too much away. I mean, and this f of d is really the c squared, where c is the recurring number. Okay, so maybe I show you the algorithm, and then we have a small break. And after that, I'll prove it to you. The correctness. So what's the algorithm? So G and sigma is given. I'll start with an empty dominating set. Oh, but by the way, just a remark that if you don't like algorithms, this is also important for people who don't like algorithms, but they like to study these notions because, of course, this shows you a combinatorial bound dependency between the two, which is also very nice for people who like structural studies of graphs. So this is not just applied to algorithms. It's nice also in the structural world of graph theory to have this kind of dependency systems. So we'll start with A to be an empty set, and R to be all the vertices. What are these three things? For this. So we'll construct this algorithm. There's a bullet time algorithm, so I'm describing the algorithm. And then I'll prove it after the break. So we'll construct D, and we'll construct I. Okay, now D will be just this D, so this will be the D dominating set. This A will not be I, it will be a candidate set where we will find I inside that. So we'll find our I inside this A. And this is just a working set where with the currently undominated vertices. This will be, we'll stop when this is reaching empty set. Undominated.
We are building both together.
Sorry?
We are building both together.
Yeah. I mean, in fact, what I'll do, I'll build D and A, and from A, then there will be another algorithm to find A, to find I inside A. So the first step is to build these three things. While there are undominated vertices, while R is an empty, what do we do? Select smallest vertex of R. We're going to say smallest, as usual, now. I think you're getting used to it. I take smallest in sigma. With respect to my ordering sigma, which was part of the input. Remember. Let's select the smallest.
Sigma is any ordering.
Any ordering. But the approximation factor will come from the weak ordering number of this ordering. So of course I want a good one for the weak ordering number of this ordering, which I can get, remember, for graphs of bounded expansion. So select smallest vertex U I add U to A, so that means this U could potentially will be in the independent set. Perhaps it will be in the independent set. And to D I add a lot of things, because I want it to be a dominating set, so I add all these weak reachability of 2D plus 1 of this U, which was the smallest in my R. So I add all of this to D. And the idea is that let's hope that this will dominate a whole lot of vertices by doing this. Of course, this is not that big in the sense it only depends on, this is basically at most C. Number of vertices, some constant. Okay. By the way, just a remark how to compute this. You can just do a BFS after you have the ordering. Because you can cut here and see what can you reach here and so on. Start to and whenever you reach these guys, so you do a VFS at that 2D plus 1, but you can never use these guys. So you remove all of these guys. I mean, this is not accurate, but you cannot do this. Whenever you do this, you stop. Anyway, this is just a side remark. You can actually compute this in polygon time. It's not that. Okay. And then what we do, now we update our R, because now we have selected all these guys in the dominating set, so we have to remove from R everybody who is dominating. Update R, that is, R becomes R minus this thing. A distance. So everybody who has a distance at most D from some vertex inside capital D. So these are the dominating vertices. I remove them from my undominated vertices. So that is my first phase of the algorithm, which computes. So my dominating set is computed like that. My independent set is not yet complete, but I have computed a candidate set, which is all these minimums of the reachability set. So after I finish, I have no more undominated vertices. So it's clear that this is a D-dominated. D is a D-dominating set. This is clear because I'm just defining greedily this algorithm. And what we have also is we have that.
You also need to remove U from R.
So U goes inside the dominating set.
Yeah.
So obviously he's dominated. So U will be automatically removed in this step. Okay, let me maybe precise the algorithm so that you understand what's going on. What am I doing? So I'm working with this ordering, right? Sigma. This is how I represent my graph. And I have some set of already dominating vertices. Looks like this. This is the dominating vertices. Inside this, of course, I have a dominating set. This is D. Everything else is in R. And inside my D, I have my A. So my A is somewhere this way.
What is it? A.
This is A. small, and you see what's going on because we select a vertex, U, we put it in A, and then we put all the weak reachable vertices, which are reachable from U, inside D. In particular, we put U inside D also. Right. So this A is really small, it is this green set. My D is a little bit bigger. And the dominating vertices of D are the white vertices here, are even bigger. That's what's going on. Everything else is R. Everything else is R, so all these parts here are undominated. What am I doing in the next step? In the next step, I'm selecting the minimum vertex U of R. It is this guy. This is my next view. And I'm doing all this business again. I put it inside A. He becomes green. Some in A. I look at the weak reachability. Well, my picture is not so nice because well, no, it's fine. In fact, this is the minimum in R. I look at the weak reachability set of U, and I put it inside D. D is perfect. So what's the weak reachability set? It's something which is, so this guy goes to D for sure, and maybe something here. So everything which is reachable here. No, it means that there is a path length that goes to D plus 1, etc. Or I can go like this. So this I add to the dominating set. So it could be that I'm adding things which were already inside, which were already dominated, doesn't matter. But now I have at least, I'm sure that I have enlarged my my A and my D by at least this U. Because this was in R. So it was neither in D nor in A. So I've at least added one more vertex. And now, of course, it may dominate a bit more here. And of course, the edges here are completely arbitrary. Okay. And like this, you go on and you grow, you dominate. This is what's happening. U is this smallest vertex U. So at each step we select a new U. What is it? The smallest undominated. So this was undominated. And it was the smallest undominated with respect to the order. This U I added to the dominating set. I added to the set A, potential independent set. And then I not just add U to the dominating set, but also all its weak reachability set. So some things which are to the left of it, I also add. So note that this weak, except for this guy, except for U, everything actually was already dominated, which I added. But I'm hoping that like this, I will dominate even further at distance D. So my R will definitely get much smaller. Something smaller. At least by one it gets smaller.
But all vertices left to U is already dominated.
They're already dominated, but they might be very useful to dominate other things. Taking that. And this algorithm is finite because at each step I select one undominated vertex at least. So there is at most n number of steps, where n is the number. So it's a polynomial term algorithm. And it is correct in the sense that it creates, at least it creates a dominating set, which is good. And now notice that this dominating set is at most c times the size of A. Why? Because at each step I select one guy, I put it in A, and the C weak reachable vertices, I put them in D. So that means I have put at most C times the number of vertices in A inside my D. So this is my first, this is a good inequality A. And so maybe this is, so I didn't give you the second phase of the algorithm will be the construction of I. Then I'll prove to you the bounds. But maybe let's have a break. 5 minutes. You can reflect on the algorithm. Let's start at 3 plus 10. It is 3 to 10. 3 plus 10 always. Since we are still to build set I, and we still need to prove the bounds. Let me see what we do. explain the claim, deduce the proof, and then I will prove the claim. So the claim is for every vertex of A, there are at most C minus 1 vertices of A. Let's go then B. So other vertices of A, there is at most C minus 1, such that B is smaller than A in the sigma ordering, and they are close. So remember that my goal is to construct a set I where everybody is a distance at least 2d plus 2, not 2d plus 1. I'm doing it because we'll get it kind of for free, so we are proving this. So I'm claiming if you have your vertex that you have selected in A, so in my picture it was the green set, right? So there is, so this A, I mean this is what I call U, right, in my algorithm. So my algorithm is like this, it will take a U, do all this business, then it will take the next U, take the next U, take the next U, and so on. This is how we construct our set capital A. We add U to A and then and at each step, this is the first, the smallest and dominating vertex. So now I'm looking at all these B's, which come before A, so that means they have been selected before by the algorithm, right? And I'm saying, there are not so many, I mean among those, there are not so many which are close, which are distance at most 2d plus 1. So maybe this is at most 2d plus 1, maybe this, but most of them are not a distance at most 2d plus 1. Most, yes. And that at most is this C minus 1. Deducing that, I mean, assuming that, assuming the claim, what do we do? You greedily select vertices of A in I. What does it mean? Take the first one, you put it in I. Okay, then the next one, maybe it is too close to this one, so you don't take it. And as long as you are too close to somebody you have already selected, you don't take them. But whenever you get the vertex which you could put in the infinite set, you do it.
So basically,
Distance is less than or greater than 2d plus 1? Distance AB?
So, what I'm saying is, whenever I look at the vertex here, among all of those which are before, there is not too many which are distance at most 2d plus 1. At most, that means most of them will be a distance at least 2d plus 1. So that means when you're here, so I can't pick this, I can't pick this, there is at most C minus 1 I cannot pick at this stage. But this guy I can pick, right? Because, yes. Wait a minute, it's the other way around. Yes. No, I'm confused. My picture is kind of the other way around. No, no. Do I go? Maybe I need to go from right to left. Yeah, I guess you go from right to left, I guess, right? C minus 1, which are smaller, which are too close to A. Yeah, I think it's this way you have to do. So you forbid the C minus 1 of them. I mean, let's make it smaller. The C minus 1 you cannot take, but the next one, this is fine. Pick it. So this gives you an independent set. I think this is correct. Maybe one needs to double check. But the idea is this. And then what I'm saying is that the I have selected now is at least A divided by C. Right? Because when I pick one, I kill C minus 1 plus 1. So when I pick one, I forbid C, I remove C from my potential set, and then I reiterate. So it's a greedy procedure. And this is, if we have this, we are good because that finishes the algorithm, because now we have, by this inequality, you have D at most CA, but we also had A, which is at most CI. Yes, so that you get C squared I, right? So you get that. D is at most C squared I, which is exactly what I wanted to do. And this is a distance 2D plus 2 independent. Of course. Okay? So this is the description of my algorithm. There are these two phases. First I build D and this A. And from the A, I can show that I don't have to remove too much. Like at most, C minus 1 by C proportion. But at least 1 over C proportion I can take in my independent set. This is a 2D plus 2. So that's the
How did you get B less than CA?
This is because when you look at the initial algorithm, when you pick somebody in A, how many, at the same time you're also enriching your D, but your D you're enriching by this set, right? But we know this is the weak reachable vertices from U. So by our assumption, it is at most C. It's a set of size at most C. Because the weak tolerating number at 2D plus 1 of any vertex is at most C. So whenever I put one vertex in A, I put at most C vertices in D. Okay, so it shows that D is not more than C times A. And then from this set A, I'm picking at least 1 over C vertices to get I. So that means D is at most C squared I. You get this. So these are the two steps of it. So now it just remains to prove the claim, right? It just remains to prove the claim. And you will see that the arguments are, it will ring a bell, it will look a little bit like what we did yesterday. So by the way, there is a much simpler algorithm, just for the, which gives an approximation for the dominating set, which I put, it was in the tutorial number 9, I guess. I think after you see this, you can try to solve that algorithm. It's easier than this, much easier. Ideas are a bit similar. Okay. Now should I do the proof? Maybe I keep the algorithm. Let's erase the theorem then. Proof of claim. So you look at your A, and let's look at the B that you have selected before. Okay. I want to say that, and let's assume that the distance between them is small. I want to say that there are not so many B's. have this property. So there is a path, since they are not too far from each other, there is a path linked to D plus 1 at most, which can be anything. It's not a weakly reachable path, it can be anything. Like that, for example. But what I know, it's called P. Length of P, I assume it to be at most D plus 1. I want to find some properties of this path to show later that I cannot be. In fact, I will show that there are not too many pieces yet. Okay, let's decompose the path into two. And what are we doing? As usual, similar trick, as usual. Let's look at the minimum guy on this path. Let's call him minimum of A. Thanks to this minimum, I can now decompose my path into two. I have PA, which is this part, and PB, which is this part, okay? P is PA concatenated with PB. Okay, so notice that this NAB, it belongs to the weak reachability set. Again, same trick as usual. It is the minimum, so it will belong to all these weak reachability sets. I mean, for B and B. Reachability 2D plus 1 of B, and also of A actually. Why? Because there is a path. Of course, this PB is smaller than 2D plus 1 because it's a subpath of P, which itself is smaller than 2D plus 1. So there is a path, and this guy is the minimum, so we are not using anything on the left. It is fulfilling the definition of weak reachability.
So PA is defined in the smallest part. What is PA? Any path?
No, PA is the subpath of PB. P, so PA. PA is this. PA is the path P from A to the minimum. Okay?
So MAB is the minimum of the path from A to B.
Yeah, it's the minimum of the ordering sigma. I'm always representing, this is always this in picture, this is my sigma. I'm ordering the vertices. I have no idea how the edges look like. I just draw my graph like this from left to right, and I put the edges, how they are.
So a minimum of all the paths or some path?
Some path. You can take the minimum. You know that there is one which is at most 2D plus 1. You take that one. Any. If you want to take the minimum, it doesn't really matter. If you take the minimum one in particular, yeah. You know it will be a plane for 2D plus 1. By my assumption. My assumption is I want to study these kind of curves. So I'm assuming this. If there is no such vertex, I'm happy. I want to show that there are not too many. If there is one, it looks like this. Okay, and this I go from M and B to B. This is the subpath. This one. Cut my path into two. Alright. Okay, now I want to say that the length of this PA should not be too small. So this is also in weak reachability. Right, this is kind of trivial because it's the minimum of this path, this path length must be this one. So I want to claim that the length of PA is at most D, sorry, as at least D plus 1, PA. Where is that?
Otherwise on D and matrix we removed the neighborhood of
This,
yeah, from R.
correct, exactly. So we know that we are processing these vertices from left to right, because we are always choosing U as the smallest and dominated. That means that B has been added to D before A. So we start, the algorithm was like this, was designed like this, that we first put B inside A and D. And now what we do, we add to D the weak reachability set of U. That means that this is in D. So this is in A and it's also in D. At this step where we have put this in A, we have put this in D. But this guy was still undominated because I was able to select it later. So that means this path cannot be at most D. If it was at most D, he would have been in this set, the dominated vertices, and I would have removed him from R. So that indeed implies that this path is not at most D, so it's at least D plus 1. Okay? Just by observing what happens in the algorithm. But that means the other path is really short. I mean, really is exaggerated, but it's at most D. Right? Because the whole thing is at most 2D plus 1. If one side is at least D plus 1, or the other has to be at most D. Okay. So now, okay, that's the situation. Okay, I have this. I want to tell that there are not so many B's. Let's assume there were, in fact I will show you that there is only one B. Like that. What do I mean by one B? What I mean is that there is only one B who shares this minimum. So now I will show that. For every A, the set of B's such that B is smaller than A, distance, exactly these B's that I defined, and this NAB for every A, for every X, NAB is equal to X. What I'm writing in mathematical style here is that, so I fix my A, I take some X, this X will be this MAB, and I'm saying there is only one X like that, which will be MAB for some B. So the set of B's, which are smaller than A, whose distance is most 2D plus 1 to A, and that share the same minimum guy here, the X, this isn't one at all. So to show this, this is easy. So suppose there are two, So if there was another one, let's see the B prime here. So that means, there would be a path prime, whose minimum is the same. And it looks like this is P prime. But I know that they intersect at this minimum. And this is the minimum of both paths. So I'm assuming by contradiction that this set is at least 2. So that means I have my B and my B prime, which have the same minimum. But then same argument as before. Because of this. We know that this path is small between this and B prime. This is at most D. That's why I proved it before. So it means when I included this guy in, I know this guy is in the dominated set. This was in A. Well, I should have removed this B prime at this stage. I should have removed him. Why? Because he's already dominated by this one. So he should have not been a candidate in A. So he doesn't exist. That's what it is. So between B and B prime, only the smallest one can exist. This is not a real vertex. This is not that. Okay? This is just because of this property. But if you had one B prime which had the same properties as B, again, you would, I'm not going too much into details, but you would have another P prime going from A to D to B prime, sorry. you can decompose it into two by exactly the same arguments. You would show that the path from the minimum towards this B prime would be at most D, which means that after the algorithm has processed B, it would have removed B prime from the set of candidates, which is a contradiction because we assumed that he was picked in A, right? I mean, our assumption was that this guy is in A. Did I write this? Yes. So this is not this. So this is true. Okay. How do we conclude from that? Well, we are done because what we have shown is that the set of these vertices here, all these B's here, for every possible minimum of the path, there's at most one, but this minimum, remember, belongs to reach-reachability set of A. So there cannot be, this set is bounded by C. So there cannot be too many minimums. There can be at most C possible minimums. Each of them gives you one other guy in B. So that means there is at most C. Well, C minus 1 because A is itself in this reachability set. So there is at most C minus 1. Okay. I'll write it this. W reach of 2B plus 1 minus 1 vertices B and A this implies this, that the number of the vertices B with these properties, which are in the claim, is at most the weak reachability set, size minus 1, because we are not counting A. And why is that? Because for each of them you will find some minimum. They are not, each minimum is in this reachability set, so that's the number of possible minima. And each minimum gives you one B at most. So you don't have too many B's. And I guess this finishes the proof. Full proof, because I showed you that using the claim now we can get the proof is complete. So I think it's quite a beautiful technique. So of course you have to be a bit clever on how to choosing these numbers for the reachability set. And then the arguments are, you see it's always a bit the same trick. You look at the minimum, try to find something. Some tricks to bound some number of vertices. It really looks a bit like what we did yesterday for the neighborhood complexity. Okay. Well, I hope you at least got kind of the flavor of this. As I said, I repeat again, in the tutorial there is a much simpler version of it, which works for the dominating set, which is still pretty nice. You can use this to get it. Are there any questions? So, and maybe now for the last end of the course, I will kind of continue hinting to other directions and maybe make sense a bit more. I think now we have all the tools to understand this picture a bit better. And I will maybe talk to you about some very recent developments, which I don't know well myself, but they seem quite exciting.
Could you tell me where the pre-depth of path is logging?
This is an exercise. So this is a classic thing. So you will find this in the book of Nechetril and Osonale-Mendes. You can find it also in the lecture notes by the Philippe Truc brothers. Nechetril and Osonale-Mendes. And the sparsity is. So, but even better, I think there's a nice proof of in the lecture notes of the sparsity series by Michel and Marcin Philippe Truc. think the link to these is given in one of the solutions to the tutorials. I gave the links. So they have a, they did this course a couple of times. I don't know if they're still doing it, but at least they put online 3 years in a row, like 2017, 2018, 2019, something like that. 2020, I don't know. And so there are these three. So I think the last one is nice. You can get the last version of the lecture notes, but the videos are from I think 2019. They're still also very nice. And you also have some exercises, tutorials. So some of our exercises are taken from them, so thanks to them. But they didn't have the solutions. I mean, they have solutions for some more complicated exercises, which I didn't take. So it was a great resource for me to design this course, to get this inspiration. Okay, let me just again just mention some things very vaguely, just to tell you that these things exist. If you want to dig more and you're interested in the topic, you can read about these things. One thing which I've seen which is used is the notion of, sparse neighborhood covers. So if C has bounded expansion, so I'm not going to define this maybe before we every graph G in C has a sparse cover, and this can be very useful in some applications. Again, I'm not sure if this is a characterization of it, but at least I've seen that they have this property. So what is this? This is a family of clusters of G. Let's say C1 to Ck. And such that what? So for every vertex in the graph, and for every, when D is fixed, there exists a cluster which contains your neighborhood as distance D. So imagine that you have a collection of these, you can kind of cover your graph here with these clusters. And now, any vertex you want of your graph should be entirely contained in one of the clusters, meaning its neighborhood at distance D. Okay. No, it didn't. But there are more conditions. So also you want that, plus you want that every vertex of V is not in too many clusters. But there is some function of V clusters. So that basically means that these clusters don't overlap too much, too many times. Essentially that's it. Maybe there are some other properties, so don't take this for granted. I think there's another property which they call bounded degree, but I forgot what it means. But what they show is that for every graph class of bounded expansion you can get these widgets, and this is used to get algorithms. I think it's used for the next thing which I'm going to mention just briefly, which is that. You remember that I told you about this Courcelles theorem for bounded tree width, which meant that every property you can do in monadic second order logic, you can write, you will find an FPT algorithm for the FPT for tree width. So what you get is a linear time algorithm to check this property if the graph has bounded period. So there is a similar theorem for first order logic, so a simpler logic, but for your graph classes of bounded expansion. And I think they use this kind of, they use a lot of things, but this is one of these.
If you had a single cluster, this satisfied, right?
Yeah, so that's why there are more conditions. Sorry, no, I didn't take enough notes. I looked at it yesterday, but I think there is a... Maybe the size of C is bounded. Sorry, yeah. My notes are, it was a bit late yesterday. My notes are not good enough. This, I just see that I don't have the moment to go first. Okay, I don't know about the boundary expansion one, but so for every first order property, P, graph property. So what means first order? First order means you have your vertices of your graph, you can have them as variables, and you can quantify over them. You can say there exists x1 for all x2, this kind of thing. But you can't quantify over sets. If you quantify over sets, that would be second order. Like monadic second order. So this is simple, first order form. But for example, you can express, I think you can express the monadic set in this language. First, P, and monotone graph class C. So P and reject in fact linear time. If C has bounded expansion. So that means you will have some function of the class and your property P and some. So this is a very strong property, which is another success story of these bounded expansion graph classes. You take any graph class of bounded expansion, you take any first order property, graph property. Now for any graph, P can be checked if, well, I didn't check for G in linear time, if so G is in your class. You can check it in linear time if your class has bounded expansion. Linear time meaning, okay, there is a huge function which will depend obviously on the class. It will basically depend on this expansion function and your property. So I don't know much about this. I just know it exists, and so this is a very powerful, strong result, which analyzes many things that were before. It was known for planar graphs and for H-free graphs, and then it was limited to boundary expansion. And in fact, it was also, so for no idents it also works. So this is by result by Grohe February 2017. So it's almost true in the sense that instead of n, you will have for more dense classes, we get a f of the class and the property times n to the 1 plus epsilon. Running time. This is for all epsilon. Choose an epsilon. You can be as close as in some sense you can be as close as linear as you want. We cannot be linear. Okay, so this is for lower dense classes. And by the way, this is for monotone. So this works for lower dense classes, but for monotone lower dense classes, they actually prove that this is a if and only if. In the sense that take a monotone graph class. Monotone means you can delete anything. You're still in the class. Then, for every first order property, you will have this kind of running time, if and only if the class was no dense. This is extremely strong. So it kind of closes the game for monotone graph classes, for the people who are looking at these kind of meta theorems. So this is quite nice. And now, now there is ongoing work to generalize this to any class, and especially hereditary graph classes. So hereditary are less permissive because you don't, or they are less permissive or more permissive. I mean, you don't necessarily allow to be stable by removing edges. You only require that you're stable by deleting vertices. So this is what hereditary graph classes are. So this works only if your graph class is monotone, so this is a stronger property.
Lower dense.
Yes, lower dense. So I'm not going to into the details, but I just want to state these things to show you that they exist, and that this is very deep results in which have an association between the algorithms. In fact, they use a lot of logic, I think, of course it's first order logic, right? So they use tools from logic, they use tools from these sparse graphs, algorithmic tools, they use these kind of things also. Many properties they use to prove these kind of theorems. And so by the way, now people are trying to do this for dense graph classes. And what they're conjecturing, so maybe you've heard of this click width. Click width is a kind of an extension of tree width, you could say, which allows also dense graphs. So bounded tree width graphs are always sparse, because they are tree width degenerate. But if you study bounded click widths, you will immediately see that you allow to have large peaks, any large peaks. But this Cauchel's theorem works in a certain way for certain formulas. It also works for bounded click width. So you also have this kind of results for dense graphs. Now this has recently been extended for first order logic also, for first order properties. It was extended to graphs of bounded twin width, which is more general than click width. Okay, so I'm not defining twin width, but it's like in the last 5 years it was studied, and it's a very powerful technique again. So in twin width what you do is you contract vertices, not necessarily adjacent. And what you do is you look at how their neighborhood differs. So if you have two vertices like this, they might. So you will contract them into a single vertex, UV. And what you do is you look at what was in common. Maybe this was in common, you're happy with it. And what was not in common, so those are the ones which are seen only by you and by me. now a single vertex. And in twin width, you do this operation, and you want to bound. You want your graph has bounded twin width. If you can do this by bounding the maximum degree in red in the red graph. This would be an entire lecture series on its own if you want to study that. But the nice thing is that these also produce very dense classes, but it also contains sparse graphs like H-minor free graphs. It contains. If you have bounded twin width, sorry, if you exclude a graph as minor, you have bounded twin width. If you have bounded clique width, you have bounded twin width. So I put this in the diagram here. If you have bounded twin width, you have bounded DC dimension. And it was proved by the colleagues who introduced this. So this was Jean Bonnet, Stéphane Thomasé, Rémi Vatrigan, and Unjung Kim. French colleagues. They introduced this in 2020. And they proved this kind of theorem for these graphs also. But now you have dense graphs. So the question is that people are trying to solve now very passionately is that what are exactly the dense graphs for which we can have this kind of graphs? And what the conjecture is that those are the graphs with which you take your sparse graphs, you take your graph of bounded expansion, you take your lower dense graphs, you perform certain logic operations on them. So it can give you dense graphs because you can create large cliques, but in some sense they come from the sparse graphs. So there's inherent structure, is a sparse graph to which you have done some modifications. And then they show that if you have this property, you also can solve your problems, in linear time or polynomial time, first order problems. Now the challenge and the conjecture they have is that this is essentially a characterization. There are no other graph classes, hereditary graph classes, which are like that. And this is going on at the moment, and actually just last Tuesday there was a paper on Array, which maybe I can show you. I wanted to show you the things which happened kind of during this course. How do I switch on? Can you help me? So roughly during this course, so in January, there was a super nice paper by Zieberts, so the same Zieberts here, who is an expert on these coloring numbers. So he wrote a survey, basically, which he has put on archive in January. So this actually helped me a lot to prepare the part on colorings.
Who would that here for every AFO graph there is cosine?
No, actually I don't know. This part I know is this, but probably this body expansion was proved before. Unfortunately, I didn't get that. And by the way, he conjectures that this is equivalent to what I said, that the graph classes for which first order logic is tractable. There is this conjecture, which is the normal. Monotically dependent. Anyway, so these are things I don't understand, but I know they are there.
You show the diagram.
So this is, you see, also January 25, so it was uploaded in January. Unfortunately, it was a bit too quick because last week. Is it fine? Oh, so this is the flip width paper. 81 pages. So this is the last version, but he uploaded 2 years ago. Last year I uploaded one of these things, and then he has this kind of diagram also. You can see bounded tree width. These are the things he talked about. Yeah. Bounded flip width. So this is nice for monotone graph classes. This is nice for hereditary graph classes. These dense ones. Okay. All right, and then last Tuesday, he and Jan Dreyer uploaded this a bit shorter 48 pages paper where he introduced merge width. And this is another width parameter which generalizes twin width. I mean, I haven't had the time to look at it, but I just saw it passing on archive. And now we get this diagram, similar diagram, but now he says that this merge width might be more interesting. So bounded merge width implies bounded flip width, but So this flip width is defined using a game, and this is more combinatorial. You merge parts of your graph like that. I think he conjectures in the paper that they are equivalent, in the sense that if one is bounded, if the other is bounded, if your graph is trajectory maybe. So this is a brand new concept. You get this nice picture of how they merge vertices to define this parameter. And also, almost 2 weeks ago, I just saw this paper, which defines shallow brambles. So they are trying to, you remember the brambles from Treewoods? So they are, I didn't read the paper, but it seems that they are defining, what could be brambles for the shallow liners. So this might be an interesting read. So you see how fast these things are developing, right? Just in 2-3 months now, you had all these papers related to this. So what I showed you is kind of a crystallization of things which happened in the last 10-15 years. But the field is now evolving towards dense graphs, as you can see, and it is very active, very, very beautiful things. This is what I wanted to show you. So you have these paths, or path forest. These are among the simplest ones. Of course, they are included in the class of forests. Right. You have, well, we can also put star forest now. We have seen that they in particular have bounded tree depth. Okay. Star forests. We had the bounded vertex cover number. So this had bounded tree depth. We just saw this morning. Okay, then you have the bounded path width. Okay. Path forests, of course. Here you have bounded tree width. And we don't have enough space. Alright, bounded path widths twice bounded tree width. Okay, if you want some specific graph classes, you have autoplane graphs, which are nice as well. They also have bounded tree width. And those we have worked with in the first tutorial. There's a question about them. This in fact, they are K4 free. We also saw that with these are in particular, this is the same as 2 trees, partial 2 trees. So I think in the first tutorial we showed that these guys are partial 2 trees, and I think Shagnik showed that partial 2 trees is the same as K4 free graphs. Okay, and they are planar. Right? Planar upon the genus. That we also saw in the lecture. Now we have excluding a minor. Maybe that we didn't see, but when you bound the genus, you actually exclude some minor. Okay. This is stronger than excluding a topological minor or excluded subdivision. Right, we have also talked about it. When you have a bounded degree, well, you certainly exclude some complete graph as a topological minor. Of course, path forests have bounded degree. Well, maybe I will miss some of the edges, but that's not a problem. Okay, then we saw bounded expansion classes, right? So they are sitting here. We saw it this week. Okay, we saw that they have bounded degeneracy. mentioned all these classes at some point or another. So this is nice. You have a nice hierarchy of graph classes here, right? That you can. There is some. These tree widths, of course, they exclude the minor. Okay, so you have this. Okay, what about bounded local tree widths? Okay, so the nice thing is now you have these local things, right? So bounded tree widths, we saw bounded local tree width. Bounded local tree width, of course, cross of bounded tree width have it, and we saw Hamilton showed that when you exclude a minor, you have this property as well. Local tree width. Oh, sorry, do you have it? Maybe you have to exclude a certain minor. I'm not sure about this one. But definitely bounded genus they have it. And actually, so this we haven't seen, but you can define the local versions of these things. So now you've understood this locality thing, is that you look at a bounded radius subgraph, and you will have a property in that. So in the same way you could define locally excluded minors. Locally excluded minor. Okay. Okay, this of course generalizes excluded minor. And in fact, this is very interesting. These bounded local tree width graphs, they are not necessarily bounded expansion. But there will be no evidence. Even though they look very structured, if I'm not mistaken, they don't have necessarily bounded expansion. And you can actually define locally bounded expansion. Locally bounded expansion, which generalizes bounded expansion. So it means that, you know, for every D, you take a subgraph of your graph of bounded expansion, of a class of bounded expansion. Sorry, of your class. For every D, you take a subgraph of your class of radius D. And the class of these kind of subgraphs should have bounded expansion. This is what it says. So it's a little bit more general. Then you have your no dense graphs. Now I'm running out of space. No dense. And of course, yeah. So bounded expansion, locally bounded expansion. No dense over here. And what we saw is that, in fact, there was a bounded declic number, if you remember. So this was I showed you, I gave you an argument that if you had bounded expansion, you certainly had bounded degeneracy. In fact, the argument was showing that if you have bounded degeneracy, you have bounded declic number. And this no dense graph also has bounded declic number. Yeah. So this declic number is quite interesting. And this bounds the VC dimension. So I also mentioned the VC dimension yesterday, 2 days ago. This sits very, very far on the top. So it's much more permissive. It allows much more things. It's quite an interesting thing. This VC dimension, if you can work with the VC dimension, you will work with all these graph classes in some sense. If you bound your VC dimension still, these graph classes bound the VC dimension. So that's interesting. You know, these things I just showed you. So then you have to do the dense ones. So your basic classes are co-graph. For this we didn't mention it. For co-graph, you have with which show bounded. Okay. In general, as I said, star forest graphs, I think. Only degree, only width. Okay, there are probably more connections, but you figure out. Alright, I don't want to bore you more, but this is maybe a global picture that you can now have a little bit, you have an idea about the connections between these graph classes. So it's a very rich world of sparse graphs that we have just started touching in these 2 weeks. And you saw it was already a lot of things. Yeah, so I guess also